energy of products minus energy of reactants. If we did that here, we'd get the same exact number here. But it's very, very difficult to calculate the energy of these particular reactants, and instead in organic chemistry, we're always making bonds and breaking bonds. In this reaction, we're going to break carbon-hydrogen bond, and in the process, in the products, we form a hydrogen-chlorine bond. So it's very easy and much more intuitive to calculate enthalpies of reactions here. We break one bond, took that much energy. When we form this bond, we liberate or get back this much energy. We're still uphill 1 kcal per mole. These numbers here, I'll provide them for you in a table. You're going to have to do a similar calculation. Maybe I'll give you methane, maybe I'll give you ethane, something like that. You'll have to set up a reaction, some propagation steps, and just look at these energetics using a very, very simple table. We're going to do the second propagation step now. Second propagation step, you'll recall, we bring our newly minted alkyl radical down here, and it reacts with Cl2. Doesn't react with Cl radical. There's not a lot of this. Not a lot of this. These two things never find one another. A little bit of this, lots of this, they find one another. On your own, when you practice this, you should be proficient at drawing a fishhook arrow here, a fishhook arrow here. I'm not going to do it now. We did it a lot last class. I'm kind of tired of it. Once you get good at it, you'll get tired of it too, and that's probably a good time to stop practicing. You're not tired of it yet. You don't know it well enough yet. In this particular reaction, I want you to overall identify what bond breaks and what bond forms. You can look at the overall reaction, figure out what bond broke and what bond formed. The bond that broke, in this case, is Cl2. If we looked it up in a table, might have an energetic value of 58 kcals per mole. That's the bond association energy. That's the amount of energy we need to break it, or if we somehow form this molecule, this is how much is liberated. But in this case, we're breaking this bond. We broke this bond. Here we're going to break this bond. The top equation, we form this bond. And in this molecule, here's the new bond we formed. And this has a bond association energy of 84 kcals per mole. The way we do the mathematics on the second enthalpy step is we simply subtract bonds formed from bonds broken, or we take bonds broken minus bond formed, and this number here, you can see, is a negative number, minus 26 kcals per mole. We can see that it's negative, which means this process is exothermic. More energy is liberated than put in. We call this the delta 2 or delta 2, or the enthalpy of reaction for the second step. So this first step process, if we look at it and calculate and do some simple calculations, this is not difficult calculations, it's subtraction. You can find these values. If you set up this reaction in blue, and you had to determine what the enthalpy of reaction is, you'd have to identify, we break this bond, you'd have to find 104 in a table. You'd have to say, oh, this bond is formed, 103 in a table, etc. Same thing down here. This bond breaks, it's gone. This new bond is formed, it's there. We add it up like this. And the total enthalpy of the reaction, H total, is a summation of H1 and delta 2H. And so the total enthalpy of this reaction is minus 25 kcals per mole. This number, 25 kcals per mole, might mean nothing to you. Well, that's okay. The one thing, though, that it does mean, and that you should know, is that this reaction is exothermic. It means more energy is liberated than what's put in, and that means that it releases heat, and it means that the products are more stable than reactants. So that's what this negative value here means. And I expect that after you practice this several times, you'll be proficient at doing it as well. Okay? You can just practice this problem in our notes. It will be enough for you, I promise, to get proficient at this in conjunction with practicing these mechanisms. So make sure you understand the mechanisms, and then overall, if I ever ask you to make an energy calculation about it, you simply have to have the propagation steps drawn, And you have to calculate and find, this bond breaks, that forms. This breaks, that forms. Do some simple subtraction, some simple addition, and we're nearly done with it. What we're going to do with this, we're going to spend 5-6 more minutes here on this, and we're going to actually graph this, and we're going to actually look at reaction coordinate diagram and what happens as this particular process happens. Absolutely don't need to memorize these values, I promise. You don't need to memorize these particular values. They'll be given to you if needed, if I give you a problem on it. So again, these numbers I don't have memorized. I will not ask you to memorize them. But if I gave you a small table with 4 energy values in it, I'm not going to give you one with 20, I'll just give you the 4 that I care about. Could you pluck out and identify, in this reaction, this is breaking, this is being formed. So it's bonds broken minus bonds formed. Bonds broken minus bonds formed. This process is endothermic, it's slightly uphill. This process is exothermic, it's very big downhill. So that's a good question. Let's actually just graph this and see what it looks like. This graph will be the basis of us understanding something more about chlorination and bromination. So we're going to make an energy diagram. We've done one already, and there's going to be quite a few in this particular class. On the y-axis is increasing energy, and on the x-axis, this is called the reaction coordinate. The thing that we could think about it is reaction progress. The reaction starts and goes to completion. What happens? Does it not have to be a work of art? I promise you mine's not going to be a work of art, and I've done it a few times. This is just a rough diagram for us to look at and visually see what's happening as this reaction is proceeding. We're going to put just some value on it. This is actually relative energy, and we're going to just put 0 on the graph. And at this 0 point, we have our methane molecule and our chlorine radical. They find one another, and there's a transition that happens as they proceed to the methyl radical plus HCl. There's a transition happens that it goes from methane and chlorine radical to methyl radical and HCl. This is the first propagation step. We start off with these two things, and the reaction starts proceeding. It's going somewhere. It's going to HCl and our methyl radical. And we already did some calculations here. We know that this is delta 1H, or 1 kcal per mole. So somewhere on here, it's about 1. Okay? So the reaction starts, it goes to this particular point. This thing, we can calculate what I'm drawing in red. And there's one other thing we're going to talk about in this particular diagram, and it's a little tricky, and I want you to listen carefully to me. This location that's very high on the graph is called a transition state, or TS. In your notes, you could write out that this is a transition state. It's something in between here, and it's unknowable, it's high energy, and we don't really know exactly what it looks like. We know with high confidence what methane looks like and chlorine radical looks like. We know what a methyl radical looks like, its geometry. There's ways to measure this. We know it's sp2 hybridized. We know what HCl looks like. But as it proceeds from here to here, when these two things approach in a collinear fashion, before they've become the products, there's some transition state, and it's not exactly known what these things look like. People are studying them. We have some ideas about them, but it's unknown what these particular things are exactly. From where we start to the top of this graph is called the activation energy. It's how much energy we need to get over this hump to get us to the next stage. This reaction, we're heating it, so we have some energy. But this is very high energy, and if this is done at very, very cold temperatures, we'll never get here. Activation energy is not something you can calculate. It's only something that you can measure. Write that down in your notes. Activation energy is not something you can calculate. It's only something you can measure with an experiment. So activation energy can't be calculated. It's something that can be measured. So I'm not going to ask you to measure anything. I'm not going to ask you to go into your bathrooms next Thursday, and do some bromination and measure anything. I don't care about this particular number if you know it. This number you can calculate. This activation energy I'll say just a little bit more about it. It can't be calculated, has to be measured, but activation energy is greater than delta 1H. So in this case, it's greater than 1 kcal. It's always going to be greater than the enthalpy of reaction, but it's going to be less than the bond dissociation energy. And in this particular case, that was 104 kcals per mole. In this particular reaction, the activation energy is 4 kcals per mole. You don't need to memorize it, not going to ask you to calculate it, nothing like that is going to happen. So we obviously couldn't calculate this. It's somewhere between 1 and 104. How would we ever guess that it's 4? We wouldn't. Someone measured that. Thankfully, they did it for me. They wrote it down, and that's enough for me. So just want to put this point here. This is about transition state theory. It's important to future study in chemistry and biochemistry, but for now, we're not concerned about the transition state and its enthalpy too much. We're really concerned about going from point A to point B. We know in our propagation step that something else happens. The next thing that happens is we have methyl radical reacting with chlorine to do something else. And this is a two-step process. So as we go from here to here, we have Cl2 combining with our methyl radical, and that undergoes some other activation energy event. And then we end up at the bottom down here. At the bottom, this is where we've made our product and regenerated our our chlorine radical. So this is propagation step 1, and this is propagation step 2. Again, there's another transition state here. This is number 2. Don't know exactly what it looks like. It has some activation energy, which is this gap. Don't know what it is. Don't care about it too much. The thing that we did that was unique is that from this point to this point, from here to here, the enthalpy dropped 26. And the overall enthalpy of this reaction is minus 25 kcals per mole. So this point right here is minus 25 kcals per mole. The numbers in red are the things that we actually calculated on the previous slide where I've been writing, and in your notes, those calculations should be there. First propagation step is uphill, 1 kcal per mole. The second propagation step releases 26 kcals a mole of energy, so it goes from plus 1 to minus 25. Okay, so from here to here, we're already up 1, then we go down 26, we're at minus 25 here. So this particular diagram is going to be useful in the second half of our lecture today, which will resume at 10:20. And we're going to do the same type of exercise right now. If this is confusing to you, we're going to do the exact same thing with bromine. So basically what we'll do is we're going to take methane. We're going to practice the propagation steps with methane. We won't draw on the mechanism, but you can do that on your own. It's very simple. And we're just going to look at some new bond association energies. I'll give us some values. We'll practice the calculation, and we're going to graph it. And energetically, bromine looks different than chlorine. And this energetic difference is what really gives rise to the different reactivities for bromination versus chlorination. So again, I know this is challenging, but as we practice it one more time, as you practice it on your own, you might get to, even, if you get to a decent level of confidence in doing this calculation, that's enough for us. You don't need to master this. But you do need to be able to do these calculations, look up energies in a table, write out a reaction, maybe write out the mechanism, and then the calculations actually become quite straightforward and simple after that. So I know many of you are panicking, seeing calculations in these crazy graphs we're drawing. Just relax for the next 9 minutes, and I'll see you shortly.